Hello. For our lab on Investigation 13, oh wait, Mr. Balicki's coming. Ah, watch out! Sorry for that interruption. For our lab on Investigation 13, we explored the effects that strong acids and bases have on bromothymol blue, or BTB. Bromothymol blue is a pH indicator that tells us whether a substance is an acid or a base according to the color of the solution. This right here is a pH test color chart. Note that when a solution is neutral, the color stays a turquoise green, and the pH is 7, just like water. As we see to the left, a solution turns yellow when it is acidic. On the contrary, as we see to the right, a solution turns blue when it is basic. In order to find the pH of the Btb solution itself, we take the antilog of its acid dissociation constant, or Ka for short, which we found online to be 1.6 times 10 to the negative 7, which results in a pH of 6.8. We know Btb is a weak acid because, as mentioned earlier, any substance that has a pH lower than 7 is considered acidic.
So we have 3 experiments of which the concentration of BTB changes, but not that of the acid, base, or salt solutions. And what we found was that the more concentrated the BTB was, or the more drops of BTB were added, the bolder the color appeared. When aqueous NaOH was added to BTB, the solution turned bluish, indicating that it is a basic solution with a pH greater than 7. When aqueous HCl was added to BTB, the solution turned yellowish, indicating that it is an acidic solution with a pH less than 7. When aqueous NaCl was added into a BTB, there was no change in color, thus no change in pH, because both the sodium cation and the chlorine anion acted as spectator ions in this reaction.
This is the reaction between BTB and water displayed in simple terms, in which the weak acid of BTB is represented by H ion. After BTB dissolves in water, it dissociates into hydronium ions and its conjugate base. The acid and its conjugate base have different colors. At low pH values, the concentration of hydronium ions is high, so the equilibrium position lies on the left-hand side of the equation, or shifts to the left, and the solution exhibits the color yellow. At high pH values, the concentration of hydronium ions is low, so the equilibrium position lies on the right side of the equation, or shifts to the right. On the screen now is the mass action expression where Kin represents the indicator dissociation constant. The change between the two colored forms of the acid and the conjugate base occurs when we have equal amounts of each. The transition or turning point is when the concentrations of both are equal. When we rearrange the mass action expression, we get this expression shown here. As we can see, the ratio of the conjugate base to the acid is inversely proportional to the hydronium ions, thus proving that the proportion of the acid to its conjugate base is responsible for the color exhibited by the indicator. In using Le Chatelier's principle, we can figure out why the color changes when we add hydrogen ions or hydroxide ions via HCl or NaOH respectively. When we add NaOH to the solution, it dissociates into sodium ions and hydroxide ions. The hydroxide ions would react with the free hydrogen ions in the solution and remove it, lowering the count of hydrogen ions and increasing the pH. This introduces stress into the system, and the equilibrium position shifts in favor to the right to replace the lost hydrogen ions and exhibits a blue color. The same overall concept can be applied when we add HCl into the solution. HCl dissociates into hydrogen ions and chloride ions, which would add a surplus of hydrogen ions into the solution and in turn lower the pH. the equilibrium would shift to the right to remove all the extra hydrogen ions and exhibit a yellow color.
So we have talked about how the indicator changes color to indicate a change in pH, but we haven't explained why this happens yet. Going further in depth, this happens because of the changes with BTB reacting with water. When in a solution with water, BTB can be protonated. It is thus a weak monoprotic acid in the equation explained earlier. BTB here can donate its H plus ions, hence the meaning of protonated, to water, which forms a conjugate base of BTB in an aqueous solution. The picture here shows this reaction in skeletal form. Notice that BTB is charged negatively on the right because it lost its H plus ions, thus is the conjugate base to the acidic BTB on the left. So when an acid or base is added to BTB, either one of these BTB reacts with the acid or the base to indicate which one, the H plus or OH minus ions, are more prevalent by color changes. Yellow for more acidic environment and blue for more basic environment.
Another way that we stress the system was by breathing into the solution using a syringe. By breathing, we produce carbon dioxide, which is then put into the solution via the syringe and reacts with water, which produces carbonic acid. BTB's most common use is to measure the presence of carbonic acid in a solution. This reaction can be expressed by this equation shown on the screen. As can be seen, hydronium ions are produced in this reaction. Thus, when carbonic acid is present, the solution is acidic and the color of the indicator becomes yellow. Only adding air from the atmosphere will not achieve the same result, as the air in our atmosphere is composed mostly of nitrogen atoms, which is an inert gas and does not react with the solution. Thus, it does not affect the pH or change the color.
And finally, here's a cool little fun fact that we found while experimenting with the BTB pH indicator. We noticed that there was a notable difference between tap water from the faucet and distilled water from a bottle. In this picture on screen, the two cups with the light turquoise color solution on the bottom and far right are the ones filled with distilled water. This makes sense because water normally has a pH of 7, and these two cups filled with distilled water have a light turquoise color, signifying that their pH is also 7. What is surprisingly odd is that the other two cups, the one on the far left and the top middle, are not a turquoise color. In fact, it is a dark blue, and when referring to our pH test color chart, we can see that having a blue color means that it is basic. That's right, our school tap water is basic and might not be the healthiest option for us. On a brighter note, I hope you enjoyed the video and learned a lot about BTB pH color testing.